All right, to finish everything out, we're going to make a few changes to the collapse cell logic that we originally had. So previously we just had an array and we were randomly getting within the range the length of this array to pick a random selected tile. Now we're going to utilize our tile options map. We're actually going to store what can exist in the first cell. So we haven't collapsed any cells, and now we're going to do our first one. It'll be at cell index 0, and it can be any option. So we're going to store that in tile options at cell index 0. Then we're going to find it. We're going to make it into an array. We're going to get the length of the set -1 for a random integer in range in the max value. So now we have 0 the length -1. The length is length 9. There are 9 options here, and then we subtract 1 to get that 8 because we start at 0 and go to 8. And then we pull off of a get from the array and get it at that index and set that to the selected tile. This will let us utilize this tile options map, as that will be a part of finishing out the updating of neighbors. We will need to remove some stuff from here. So we want to make sure that we have things in there to begin with. Next up, we are going to set aside the adding of the collapse cell, and we're going to move that down somewhere later. This is not going to occur right after we select a tile any longer, as we only want to add it to the collapse tiles map if we know for certain that everything has worked out and that it is definitively going to be the tile that we've selected. And why that might not be the case is we can see here I've created a collapse graph of everything we went over in the last video, with the addition of some new information off of the invalid neighbors pin. This is going to cover when we have some of those cases that might break or be unsolvable. So what we're going to do is pull off the invalid neighbors. We want to clear that map, the neighbors options map, and then we want to use the set ref. This was set back here. This gives us whatever tile options can exist at a neighbor cell. Then we want to remove the selected tile from that set ref. So what would be going on, if you remember in about 2 videos ago when I was explaining some of the logic behind forward checking, is if we were to be collapsing this specific tile, there are 2 options that could exist here, this tile as well as this tile. Now, if we didn't do the forward checking and we collapsed that tile, this would now create an unsolvable scenario. There's nothing that can go here or further here that will complete this map. So we would need to make some type of logic that would, before completely collapsing this, it would check and see if there's going to be valid options here and here, if there'll be valid options here and here, and if they're not, we're not going to collapse it, and we're going to move on to the next option and try that. And if that one wouldn't work, we would continue iterating through all of the options to see if one will work. And if none of them works, then we'll backtrack and completely restart and try again further back in the whole wave function collapse. But in this case, we know this cell would work, and we would then be able to finish out our graph. So that's what we're doing. We're removing the bad actor, the bad tile. And then we're going to check to make sure that after removing this, we're going to see if the set ref is now not empty. We want to make sure it is not empty. If that's true, we're going to do more stuff. If that is false, this is where we're going to backtrack. However, we don't need to worry about backtracking right now. That'll come in a few videos. And that adds several layers of complexity. Then, now all we need to do is, now that we've removed something from the set ref, we need to go ahead and re-add it back at the current cell index, as that is where we are getting the selected tile. Remember, that's coming from back here again. We've gotten it, we've added it initially, and now we found one that didn't work, so we're adding in the reference minus the impossible tile. And then we need to just have an output to something like try new tile. And where this will go, it will pull all the way back to this array. And then we will be able to try again and get a new tile from the now shorter range. So all of this will work dynamically with the removal of tiles that will not work. Okay, now we're going to continue onward. So if nothing like that happened, if everything worked as intended, there were no impossible scenarios or situations, we will then use the completed pin. So we need to have completed connected to completed. And what we're going to do is also make sure we have the break bool as an output. And in fact, if you don't know how to change collapse graphs or even make collapse graphs, I should have said you can right click collapse to nodes, any number of nodes, and then work from there. So you could select a whole bunch, collapse to nodes, and then you can add exec pins and booleans all in here. And so we'll need the break bool to also be connected over here to the break bool. And we're going to make a branch check to make sure that we have not broken. So if we have not broken, if that's true, then we're going to update the neighbors. And that'll be done by getting the neighbor options map, turning it to keys. I don't like that it's a fast for each. I had been messing around with potentially faster for each loops. However, they're a little dangerous, so we're not going to use them. And what we need to do is just for each loop, set the array element to be the neighbor cell index, that local variable that we already have. We can reuse it. And we are going to then find that index in neighbor options and promote it to the local variable setref. We can reuse this one too, as well as find it within the tile options. So this is neighbor options, this is tile options. We're going to see here that we need to do a branch if it exists within tile options. So we can read here, if the neighbor cell index exists in tile options, then it has previously been added to the entropy array and was updated in the past. If it does not exist within tile options, then it will not be in the entropy array. It is its first time being updated, and we can skip trying to remove it from the entropy array, which is what this will do. So if it's true that we find it, we want to remove from entropy array, use that macro. If your macro is not working, make sure you go into the macro library and that the array is set to whatever the type, the int array or type for your entropy array is, as that may differ if you've named it something different. Then we need to have tile options map just be the tile options, and the cell index to be the neighbor cell index. And what this is going to actually do is it's going to find that cell. It's going to get its length, because we use length to store based off of entropy. However long the set is going to be its entropic value. So if it has a length of 4, it has an entropy of 4. There are 4 options. If it has a length of 9, it would have a entropy of 9, because there are 9 options, and so on. And so based off of that original creation of the entropy array, we can remove it from that array index, because we made it in such a way that there would always be an entropic value, an entropic index for any potential, the longest lengths that would exist within our rules. And so we'll just do that, and then we need to pull off of the integer, the int array, and find the same cell index, and then remove it from the int array. And this will all automatically add into here, or it will automatically remove, because we're using a reference, a get reference, and not a get copy in this macro. Okay, the next thing we need to do is then, and we pull out the false, just goes around. We don't need to try to remove it, as I just explained. Next thing we need to do is now add in the new options into the actual tile options. So we promoted the options within the neighbor options, and remember that was made in the forward checking area. And now that we've passed the forward checking, that's all clear. We're going to use this tile set and we're going to add it into the greater tile options, as this is now determined that it can absolutely exist there. So we will just add it at the neighbor cell index, and then we need to add the neighbor cell index into the entropy array at the entropy of the options, which are, it's just the set. So its length, it will be how it'll be its we'll just keep calling it its entropic value, its entropy, and we will add it at that index, and then add the neighbor cell index into the indexes or indices array. Now, it's a little weird to understand this. I tried to explain it in the video where we made it, but essentially this is just creating a sort of priority queue with a nested array, where the greater array stores things based off of entropy, and the inner array, this one right here, will then store the cells indexes in the order that they're added. So then we can get the highest priority, being the thing that was added into here first will be the highest priority for what needs to be collapsed next at whatever entropy array. And we'll see that in it'll probably be, it might actually be the next video where we propagate our collapse, and we need to find what cell needs to be collapsed next. What is the highest priority, lowest entropy? And that's how this works. It might be a little bit confusing. It's kind of an interesting form of a data structure. Okay, so we've added it now into the entropy array. You can go back here. Once that's completed, iterating through all of the different keys, we're going to now remove our current cell index, our original cell that we just collapsed. We need to remove it from the entropy array if it already existed in there. Now, in the case of the first cell, it wouldn't exist in there, but that only happens one time. So we're going to not add in a redundant, we're not going to add in any type of branch to check, because this will only occur once, where the first cell is not in the entropy. So this is the first cell we've collapsed. Technically, it will not already be in the entropy array. However, that literally happens once per the entire wave function collapse, so it's not worth checking a Boolean every single time because it happens once. And the macro will, I guess the macro doesn't. Okay, that's a little problematic now that I look at it. Well, I don't like that. All right, fine. We're going to add in a branch check. We're going to find, this is just safety. We're going to add in more redundant measures to make sure nothing breaks. Because what's going to happen here, now that I think about it, is that we're going to run this macro because this cell index doesn't exist within the entropy array, but we don't have any safety measures within here. It still could try to remove an index. This find, it's not a branch check. It's going to find, it'll probably output a 0, and then it will try to remove a 0, and that could be problematic for just some memory management. So we're going to add in that check. Even if it's fired once, it's worth not breaking literally everything. So as long as that's true, that we find it, then we will remove it. If it's not true, then we will just continue onward. And continuing onward, we now need to remove the cell index from tile options, as it is now going to be a collapsed cell. It is not variable. There is not any potential for different options. It has now been collapsed. And remember, I've mentioned a couple times now the difference between these two. These two work together but are very different. Tile options are cells that have not been collapsed, that have multiple options, collapsed tiles are collapsed. They have been determined and given a set value. So now that we have collapsed the first cell, it's passed all of our forward checking, it didn't backtrack, it's everything's worked out. We now need to say that it has officially been collapsed and remove it from the tile options. Okay, perfect. So that will be everything for the updating of neighbors. I hope that, and that this is, remember I said set this aside for later. We've put it over here now. And I have my debug print that I showed in the last video. It's purely for debugging using appends to see what different options are. And you can just kind of glance at that. It's not necessary. Okay, so that will be all of the updating and forward checking to make sure everything is working and we can run it. And we'll see that right here, ground 4, top right, right, that is correct for the tile that I just saw. And to the right of it is top middle, top right, and left dot, which is all correct for this cell. So we know that to the right of this cell, there are now set options that we can then pick from, and above it, there are set options that we can pick from. And that will allow us to propagate a collapse until it is completely filled out our given chunk size. Oh, look at that. We've got something that's broken. Oh, that's right. I gave bad information. Well, that's interesting. We're gonna do some quick debugging. We're gonna actually, I feel like I've missed something from my actual. That's so strange. That normally doesn't break. But it makes sense why it's breaking. So we're gonna fix this real time. Okay. We're gonna just do it if we can get a better accurate check. We're gonna do collapse cells length is equal to 0. That means there's not been anything collapsed yet. And we'll actually do if it's not equal to 0. So that means any other than 0 will be true. If it is 0, that'll be false. And we'll see, we will no longer get that error. So there was a little bit of live debugging. I think I don't usually pull that error because I run on a separate thread, and that's kind of bad. So this is a great catch while I'm doing my one take. I hope that makes sense. Please feel free to ask questions as always, and we will continue onwards with the actual propagating of the collapse, which will then be followed by adding in tile weights, adding in seeds, and then we will do some backtracking. And after that, that will be almost a complete, that should be about a complete chunk. So then we can start to affect the chunk neighbors and then propagate a collapse across chunks and begin to create a world. So this has been a bit of a 4-part for updating the neighbors. I've tried to keep things simple, typically 1 video per part in the wave function collapse, but this is more complicated. So I hope you've watched through each video. Thanks. Goodbye.